Hello, I'm Dr. Kathleen Schmidt from Lawrence Livermore National Laboratory. Welcome to the Data Science Institute's virtual seminar series. With Lawrence Livermore being home to many challenging data sets, as well as some of the world's most advanced supercomputers, data science has become an essential discipline in the lab's key program areas. The DSI acts as a central hub for the lab's data science activities by fostering collaborations, promoting research, and engaging in outreach activities. Our DSI staff work in a variety of areas, including artificial intelligence, big data analytics, computer vision, machine learning, predictive modeling, statistical inference, and uncertainty quantification. The DSI hosts events like this seminar series to introduce new ideas and potential collaborators to the lab. We invite speakers from other institutions, both from the Bay Area and beyond, to share their innovative projects, approaches, and ideas with our data science community. We're pleased now to include a wider audience beyond the lab to engage with us through this series. You can read about past speakers on our website, data-science.llnl.gov, or email us at datascience@llnl.gov. Thank you, and enjoy the seminar.
Thank you so much for inviting me. Thank you everyone who's tuning in virtually to hear about my talk. I really appreciate it. As you can see from the slide, the title of my talk is Deep Generative Modeling in Networks with Applications to Public Policy Research. Maybe I can announce this. Essentially with this talk, what I want to do is I want to talk about some interesting problems in network science that arose in the course of the sort of public policy research that we do at the RAND Corporation and that I've been involved in. And some of these problems are rather tricky, and they involve manipulating large data sets. And so I think it's natural to ask, given all the excitement and all the advances that have occurred in artificial intelligence and machine learning, it's natural to ask if there's anything we can use from these recent advances in these types of network science problems. So the talk is going to be about trying to apply deep generative modeling advances in machine learning to these types of network science problems that are motivated by public policy concerns. And so you might, there we go. You might ask why the focus on public policy. And so I'm sure some of you on the call know what the RAND Corporation is, but I don't want to assume that everybody knows about it. So I thought I would just devote a single slide to sort of some general background. So here's a picture of RAND. This is our headquarters in Santa Monica, and I'm just down the street from that, broadcasting from my apartment. RAND is an acronym that stands for Research and Development, but sometimes people joke that it should instead stand for Research and No Development because we don't actually develop any products or build anything. What we essentially are is a nonprofit, nonpartisan research institution, which is commonly called a think tank. And essentially what we do is we carry out research into a broad range of policy areas. And we're known for our multidisciplinary approach and for giving people the opportunity to sort of take skills that they learned in one area and then apply it to another. And so I'm a perfect case study of this given my background in black holes and physics. And today I'm talking about applying machine learning to network problems. Okay. So RAND is a think tank that houses 4 different FFRDCs. Those are known as federally funded research and development centers. So these are very different than the sort of national lab FFRDCs like Lawrence Livermore. These are institutions that do research that's dedicated towards a particular government agency. So we have one for the Air Force, Army, DHS, and the intelligence community. And much of our work comes through those organizations, but we also do work for other funding agencies. And in particular, we have a lot of research funded by a RAND health unit. Okay, so that's just one slide of the background. Everything I'm going to talk about today grew out of a 1-year project that was internally funded. So we're on the fiscal year cycle, and this was a fiscal year 20 project. Many projects that we do at RAND, most of them actually are funded externally, but sometimes we will fund internal projects to sort of develop methods or capabilities that we expect will be useful for future projects. And this one was sponsored by the RAND Health Unit. I had a really excellent team with me, and I'm showing all their faces and names here. I was a co-PI, and I did this together with Rafael Vardavas, who also has a background in physics. And essentially what this is an exploratory effort aimed at developing new methodologies and software tools for the sake of future network research within RAND. What I'm going to talk about is all encapsulated in a working paper you can find on our website, and we also uploaded it to the archive. And although the official project has ended, we've encountered a bunch of interesting spin-offs that are resisting our efforts to let them go. And so we'd like to have a few forthcoming technical publications devoted to these different areas. But this is an ongoing effort, and we'll see how the funding works out. Before I launch into the main part of the talk, I just want to say that if people find anything I'm saying interesting and they don't get to ask questions for some reason during the Q&A, or the questions are more involved than a Q&A would allow for, please send me an email, and I'm happy to talk about this later offline. Okay, so with the outline of the talk, it's a very simple outline. I just want to really do two different things. I want to introduce a handful of network science problems that are motivated by the sorts of public policy research we do here at RAND. And hopefully I can convince you that these are interesting problems. And then in the second part of the talk, I'd like to bring in some recent developments in AI and machine learning and talk about how they can be used to address these problems. And this is, I'd like to think of this as a work in progress. We have some interesting results, but a lot of the work I think remains to be done, and so hopefully it'll be an ongoing conversation moving forward. Okay, so for the first part, public policy motivated network problems. It's probably not surprising if I were to say that networks are ubiquitous in the course of public policy research. Probably that's not surprising to you because I'm guessing ubiquitous in whatever your particular research area is. The reason networks are so ubiquitous is it's essentially the goal of the whole theory, the whole industry of graph theory. So if you just take a moment and go back to Euler, looking at this interesting bridge problem in the city of Königsberg, which is now, I already forgot it. I think it's Kaliningrad in Russia. There was this interesting problem that really this was just a pastime where people would ask themselves, is it possible to cross every bridge in this city just once and visit every landmass? And Euler solved this problem. And in solving it, he realized that many of the details of the problem weren't relevant. It didn't matter that this was a city and that there were bridges going across the river. What really mattered was just the abstract structure of a graph or the network. And his solution of this problem, it's interesting to go back and read it. I did that in preparation for this talk, and it's generally accredited with the beginning of graph theory. And in that same spirit, there's many interesting problems that when you abstract away the details that aren't relevant, what you are left with is a network of some kind. And indeed, this is true in public policy. And it's been true in public policy for a while. And I just want to focus on some areas that it's really interesting and research is happening on today. So, one of the main areas of interest is social networks. And so if you're interested in disinformation and how information, whether it's true or not true, might propagate over a social network, you'll have a network in this case of where people comprise the nodes and the edges are some sort of virtual connection between people. Maybe they're friends on a social media platform. The thing I think that's really at the tip of all our minds is the contact network relevant for epidemiology. So in this case, it's a physical social contact network where two people are connected if they happen to be within some short range of each other in physical distance for an extended period of time. The reason why that's relevant is because, of course, that would allow COVID to spread from one person to the other if one of them happened to be sick. Economists can be interested in networks at RAND. They're used to model supply chains, problems with logistics. You can try to model economic crises. And then, of course, it goes without mentioning that the most famous network of all is probably the internet. And so anyone interested in cybersecurity or cyber policy, networks are very relevant for these types of researchers at RAND also. And just to kind of underscore that this is not a new phenomenon, this is a really, essentially this idea of looking at networks has been with RAND almost as long as we've been an institution. One of our more famous publications here, I'm showing a figure from it on the bottom by Paul Baran on distributed communications. He was looking at how a communications network can be resilient or vulnerable to attack based on the network topology. And you know, it's very similar questions can be asked about breaking up the spread of COVID with different social distancing measures or intervention measures. And so the idea of abstracting away the details that are irrelevant and getting you know, an underlying network problem is very powerful and it connects these two very different application areas. Okay, so everything I talk about, with the previous slide, what I meant to convey to people is that there's a lot of areas where networks are important at RAND, but what I want to do with this talk and what we did with this research project is really just focus on one single area. So this is the area of epidemiology. Now, just as a full disclosure, I don't have a background in epidemiology, and I'm very much a newcomer to this, and unfortunately, I've had a reason to become interested in this because of the pandemic we're all suffering through. And I'm guessing many people in the audience have become a little bit familiar with this field just out of scientific curiosity. So if you wanted to start doing some sort of epidemiological modeling, probably the simplest thing you could do is a compartmental model. And I think the most famous of these is the SIR model. So in this case, what you're trying to do is, rather than model every single person and the health of every single person, you're going to assume that the disease has a very simple progression. There's 3 states a person can occupy: susceptible, infected, or recovered. And you're not going to look at trying to model the state of any one person, but instead you're going to model like how many people at any one moment are susceptible, how many people at any one moment are infected, and so on. So it's a very gross type of modeling approach. The benefit of this is that it's very simple. You can write down a series of differential equations, and it's essentially trivial to integrate them. And so this is a very easy thing to do. You can change your parameters and rerun the model in no time at all. And simple and very intuitive. Okay, so but of course this falls short from modeling a real-world disease like COVID. And there's 2 kind of obvious drawbacks. The first is that COVID certainly isn't well described by an S to I to R type of state transition. It's much more involved. There's many more pathways. You can be infected but asymptomatic. You know, and you could try to expand your model to incorporate all this detail. And another area in which it's insufficient, which is completely orthogonal, is the fact that this assumes a uniform mixing. And the modeling approach is just capturing these entire subpopulations. A more sophisticated but also more tricky thing to do would be to have this physical contact network I mentioned before, which you can think of as like the underlying lattice over which this disease propagates. And then you can, for every single node, you would have a state, and you can have a state transition from S to I if an I node is in contact with an S node. And you'll flip a coin to see if that person actually does get sick. And you can do what's called a network-based microsimulation to model this. And this is a much more flexible class of models, and so naturally you could do a better job capturing reality. But of course, the flip side of that is it's harder and more computationally intensive. The other issue with this type of approach is you need this network to begin with. You need to know how the population you're studying is connected. And sometimes you have that information and sometimes you don't. And so this becomes questions about how to get this data set and how to manipulate it and process it become really important for all of these modeling approaches, which will then use that network data set to study COVID, to study vaccinations, all sorts of interesting questions. Here I'm going to talk about one particular data set that is quite popular within the field, and we used it for our report and our study. This is the NDSSL Transim data. Okay, so what is this network? Well, it's a data set that represents a large-scale social contact network of the people in Portland, Oregon. So the picture I'm showing here is just like a notional or schematic picture. It's not the actual graph, but it does capture the idea that you have a population of people within this the borders of Portland, Oregon, and they're connected based on how we think the actual residents of the city would be connected. The nodes are people. The edges represent people that are tied in some way. And importantly, we actually have more information than just the graph in the sense of the vertex set and the edge set. We have, in addition, we have data entries corresponding to demographic data. So for example, we know the age, gender, whether or not someone is employed or not, and actually a long list of these types of demographic variables. And we also have variables associated with the edges. So we know how long were these two people in contact for, and essentially what was their business when the interaction happened. Were they both going to school? Was one person going shopping and the other person happened to work at that shopping mall? And so this actually motivates the need for a new type of data object, not just a graph, but like an enhanced or augmented graph, where in addition we have a vector for every node and a vector of attributes for every edge. And if you stack all those together, you can have a matrix of attributes for the nodes and a matrix of attributes for the edges. And so this is what we call an attributed graph. And this is essentially the main data structure that all of our machine learning approaches will manipulate. Okay. I'd like to give you all just a taste of what this data set sort of looks like, some intuition. I can't just show you visually what it looks like because it's too large. It has 1.6 million nodes. This is a large graph or a small graph, maybe depending on who you ask. I think if you were to go to a tech company, this would be quite modest, but many of the early papers that were extending neural networks to graph structured data, for those types of papers, this would be a very large network. 1.6 million nodes, and there's 20 million edges. And here's some statistical plots I'm showing here. Of course, there's many things we could look at. So this is just meant to give you an imperfect intuition for what the graph looks like. The first thing you might care about is the degree distribution. And it has this sort of bimodal property here where there's lots of nodes with low degree. And then it starts to, the density goes down. And then there's lots of nodes with an intermediate degree of about 40 or so. And if you look at the tail, it has a fat tail, but we did a statistical test and found it's not actually a power law. So this thing is not asymptotically a scale-free network, which are networks that are quite popular in the literature, but it does have this type of fat tail, which is really important for things like how the disease will spread among a population. And just one other example of a network statistic you might care about is for a given node of degree k, what is the average degree of that node's neighbors? And so that's the thing I'm plotting in the second picture to the right as a function of degree. And the fact that this is a positive, there's a positive correlation between these two quantities means that this network is assortive in the sense that people with many connections tend to know other people with many connections. And that's also an important property if you want to understand something like any sort of dynamical process that plays out over this network. And in addition to trying to understand the network statistics, we also have distributions of these feature variables for the nodes and the edges. But I'm going to stop here and look at sort of the chain of logic for how these could be used. So you start off with a network-based microsimulation model. Let's say you want to do a really interesting and involved simulation of how COVID or any other disease might spread across some population. Okay, so that's your starting point. To do this, you need a network in order, because this is, the network will serve as the lattice over which this process plays out. And so the next question then is, okay, well, where do you get that? And that's actually a really interesting, set of questions. You could try to go out and measure this network empirically. And I don't talk about this in this talk or in our report at all, although I just want to make a shameless plug for a paper we have coming out, hopefully any day now, with one of my co-authors of this report, Rafael Vardavas, and a few other RAND researchers, where we looked at cell phone data and we used that to infer when two people were physically close to one another at the same time, and essentially backed out a physical contact network in that way. There's another approach, which is to use some sort of artificial network. Like you might assume, okay, I'm going to use a scale-free network, one of these mathematical like toy models of random networks that you would find in the literature. You could use a data set like the NDSSL data set I just talked about. Whatever you use, you have to find a way of answering this question. Once you answer it, unfortunately, often that just isn't the end. Often the way you've answered it means that your data set is incomplete in some way. So for example, if you build a network using cell phone data, you'll have a really wonderful network in terms of who is connected to who, but you don't have the demographic variables for each person that you might want if you're trying to, you might need these variables depending on what modeling questions you're motivated by. You don't know the age of the people, so this would be relevant if you want to study, the death rate, because that's going to be affected by age. You don't know their income level. You don't know their socioeconomic situation. And so the data set is going to be likely be incomplete in one way or another. And essentially all the data science approaches I want to talk about are motivated by that third box here, how to enhance or improve this situation. And so that motivates new methodological challenges. Okay, so this is really like an open-ended point where you could come up with all sorts of different challenges that might arise in a different problem that you're interested in modeling. And for the sake of this report, we organized them into four main categories of problems. And so I want to just spend some time introducing these. And I'd like to think that these are sort of universally interesting and might be relevant for many other areas of research. But they certainly were showing up in our research doing epidemiological modeling. Okay, so the first class of problems is network rescaling. You have a graph or a network representing a population, for example, Portland, and maybe you want to either scale it up or scale it down. Maybe you want to model like a larger metropolitan area, so you want to make the graph bigger. Maybe you want to model just a single township. And there's a lot of information in how people in this area are connected to one another that you would like to carry over, but now you just want to change the network so that it's either bigger or smaller. And the question of what is held constant as you do this process will, of course, affect your solution to this problem. But without getting into, further specifying it, this is a class of problems that came up quite a bit. Another one that was even more prevalent that we encountered was this problem of imputation. So just for the sake of argument, imagine that for whatever reason, your data collection approach failed in a given zip code. So you have the entire network of your population, but there's a hole cut out of it. And you don't know anything about the people in that hole. Maybe census data, so you might know like the demographic distribution within that zip code. But you don't know how they're stitched together with the rest of the population. And so as an imputation problem, you would like to generate, these artificial people and then connect them together. Another one would be, could you take a given data set of a single or maybe even multiple networks and generate an artificial network? This could be useful if you wanted to anonymize a data set, or it could be useful if you wanted to generate an ensemble of statistically equivalent networks so that you could do some sort of sensitivity analysis. And then the last question is also quite broad, but we had a specific example in mind when we started thinking about it, which was, imagine if you have a very accurate global representation of the network, for example, with the cell phone setup I just described, where you've really done a good job capturing which people are connected to which other people. But unfortunately, you don't have a lot of insight into like the nodes or the edge attributes. You don't know the people's age. You don't know their income. Well, what RAND actually is really good at doing and has been doing for a long time is going out and conducting surveys where we ask people this like long list of detailed questions, and then we ask them to give information for their people in their network, their like immediate neighborhood. So what we have actually is these two types of data sets that are both, really insightful, but also very limited, but in complementary ways. So we have this, the global view of the network, but we don't have any information about the nodes or the edges. That's on the one hand. And on the other hand, we have a lot of information about these little islands, or we like to call them egocentric networks. And the question is, can you take these two different complementary data sets and fuse them together so that you have a more accurate and complete representation of the full population? Okay, so we call that the network fusion problem. Okay, so that's the 4 problems I wanted to talk about. And at this point, I haven't really said anything about artificial intelligence or machine learning or any fancy algorithms. And so now I'm going to start talking about that aspect. How can we take some of these recent advances in AI, and there have been a tremendous amount of activity in this area. How can we exploit these to try to address these problems? Okay. I'm guessing many people in the audience understand neural networks very well, so please don't feel insulted that I just want to spend one slide going over what they are, how they work. And the only reason I'm doing this is because it'll then be very easy to see how you can expand upon this simple and common framework for the regular neural network or the vanilla neural network and promote it to a network that can handle data with some sort of graph structure, like these types of contact networks I was just describing. Okay, and we have a pictorial description and a description in terms of equations. In terms of equations, we have these data points, x, which are the x's, and the I index just tells you which data point you have, 1, 2, 3, whatever. And to apply a neural network to this data, you just do a linear transformation. So you hit it with a matrix and you add a bias vector, and then you apply a nonlinear, a pointwise nonlinearity, which people call an activation function. That's a very simple transformation. And then the basic trick in all of deep learning is to just repeat this. And you repeat it many times. Each of the times you repeat it, this is called adding a layer to your neural network. And the end result is you get this large family of functions that are acting on your data. And the parameters of this function are the W matrices and the B vectors. And people have proven that if you are able, this is within the space of parameters, it's a really large parametric family capable of approximating essentially arbitrarily well any function you might have of interest. And so the goal is then just to train these parameters on some data set so that the function you learn is useful for some task, like classification or regression or something like that. Okay, so it's a really it's a very obvious point, but here when we look at the data, they're just isolated data points. So like in this case with the picture, they're 5-dimensional vectors, and there's no sort of relationship between them. I have a data point 1, I have a data point 2. There's no sense in which data point 1 and 2 are connected or relate to one another. Okay, so what I want to talk about is how might we extend the simple paradigm of neural networks to a scenario where that's not the case, where, okay, we have these different data points, but we know that there's this underlying structure of relations that connects them. And so you go from a data set to an attributed graph being the data set. An example of this would be like the contact networks I just was talking about, where maybe the nodes are people, and each of these little dots associated with the node is like their age, their race, their yearly income, any sort of number that further characterizes that node. So this leads to a whole subfield of machine learning that has a few different names. Sometimes people call them graph neural networks. Sometimes people will say graph machine learning. You'll also hear often graph representation learning. Whatever name you want to use or how you decide to define those terms, there's a whole industry of machine learning that is really generating a lot of activity and interest. And it's essentially aimed at addressing this problem of how to take neural networks and apply them to these types of structured data sets. Okay, so the figure I'm showing below is a bit of a mess. It may or may not be useful for you. What I'm attempting to illustrate here is how to take the simple neural network, the feed-forward pass through the simple vanilla neural network, and extend it to a scenario where now we have data that has relationships between the different data points. And so what you see is that we still retain this concept of different layers, where you're moving the data through processing layers and you stack them together to form a big neural network. But what this figure is trying to depict is that in order to compute, for example, the representation associated with data point 1, you need to also combine that data with the data for point 2. And this is because point 1 and 2 are connected in your data graph. And so your computational, the feed-forward process of the neural network no longer acts kind of in parallel and independently on every data point. Now it involves transmitting data from one node to another node and aggregating those two data points in some way. It could be simple addition, there could be more complicated operations, but it's essentially that basic idea of combining data from neighboring nodes. To say it another way, the basic design principle of a graph neural network is that you want to incorporate the network structure of your data. At the same time, you want to be constrained in how you do so. You'd like to preserve the network structure. And I think the way of describing this that's probably appealing to physicists is that you would say that the forward pass through the neural network of your data set should commute with a graph isomorphism. In other words, if I scramble up the nodes and I change their ordering, that's kind of a superficial change to my graph. I'm not changing it. I'm just relabeling which node I'm calling node 1 and which node I'm calling node 2. And that should, whether or not I do that, if I apply the data to the graph neural network, I should get the same result. Okay, so there's actually many ways of doing this, and it's a very active area of research right now. To show you just one example of how it might work that I think is really simple and clear, here in equations, I have two different approaches. One is multi-layer perceptron, which is just another name for the vanilla feed-forward network I had before, which is not a graph neural network. And then I have the graph sage equation. This is from a paper by Hamilton and co-authors. And the only difference between these two layer relations is that this middle term here, where you're summing up the embedding vectors of all the neighboring nodes. So if you want to compute the vector for node I, you look at the nodes, the vectors for the neighboring nodes, which are j's, and you add them all up. Then that thing has a new weight matrix applied to it and a possible weighting term, which is this w with a subscript. And then you add that into the activation function. And so that's one very simple way of incorporating this graph structure. And these types of approaches have shown to really far outperform standard neural networks when the data has an underlying network structure to it. Okay. So obviously these graph neural networks are only useful if you can use them to solve interesting problems. And so one major class of problems is link prediction. So this is a very timeless problem that people have thought about in computer science and statistics, where you have a graph and you observe some edges, and then you observe the absence of other edges, but there are certain pairs of nodes and you're not sure if those are actually connected or not. And the question is to make a prediction there. If you think about this in terms of the adjacency matrix, which if the graph is undirected is symmetric, this is like saying I have a matrix of ones and zeros, but then some of those entries are obscured from me, and I'd like to predict them. So it's just a type of binary, a binary classification problem. So there's many approaches to solving this problem. I think the simplest one that involves a graph neural network is probably the graph autoencoder. This was done by Kipf and Welling a few years ago. And what they do is they use whatever graph neural network architecture you might like. It could be graph sage, it could be graph convolutional networks, any of them. You compute these the z vectors for every single node. So you push the data through the neural network to get this new set of vectors for every node. And then to determine whether or not two nodes should be connected, you just take the dot product of their vectors, their learned representation vectors. That's going to be some real number that could be positive or negative. It'll be large and positive if they're parallel, large and negative if they're anti-parallel. And then you insert that into a sigmoid function, and that is your estimate for the probability of that edge being present. When you do that, when you start off by doing this without training your neural network, this is just going to be some arbitrary number. It's not going to be correlated in any way with whether or not that edge is actually present. And then, of course, you can train the model parameters, the weights and the biases, using the cross-entropy loss function, because this is indeed just a binary classification problem. And eventually, your model will do a good job predicting these missing edges. All right, and you can go and look in these these are some of the early papers in the graph machine learning literature and see just how much better the graph neural network does at this task than the standard multi-layer perceptron. And so that's kind of like a evidence in favor of these types of neural network architectures. One issue that we ran into in just trying to straightforwardly apply this link prediction approach to our data set is the issue of graph sampling. And actually, we spent, I would say, the majority of our time on the project thinking about these types of questions. So the issue is that many of the graphs of interest are quite large. The graph we had was about 1.5 million nodes big. That means that the adjacency matrix has about 10 to the 12 entries. And so there's no way that can fit in memory. So you have to be a little bit more sophisticated with how you implement the algorithm. Obviously, you'd like to use the edge list instead of the adjacency matrix. But actually, for these types of data sets where the edges have attributes and the nodes have attributes, in our case, we had 20 million edges, and that was still rather large to handle. And so you have to break up the problem even further. What we did is we tried different sampling approaches to try to break up this big graph into smaller pieces that we could then apply the neural networks to. One of the main headaches associated with this is that, as far as I'm aware, there's no way of doing this that does not introduce bias. One way of doing it is a snowball sample. That's this figure I'm showing on the top right corner, where you pick a few seed nodes at random, and then you go outwards to pick up their neighbors, and then it may be the neighbors of the neighbors. And this is called the snowball because it's sort of growing outwards in a breadth-first search type of manner. But that's a very heavily biased sample. There's some other work in the literature where people have tried to address better ways of doing these sampling problems. The one we found that we really liked was the graph Saint random walk, where you're doing a random walk on the graph, and in order to try to correct for the biases, you can do many random walks to get an estimate of, how certain nodes are being oversampled or undersampled, and then you can correct for that. But this is not a perfect procedure, and even that has its own bias. A completely separate, but also very frustrating issue you have to deal with is that there's a very significant class imbalance problem here. With 1.5 million nodes and 20 million edges, the graph is very sparse. So if you were trying to do a link prediction task, you could do a really good job just by always predicting that the edge is absent, because almost always it will be. And so if you were to do that, it doesn't mean you've actually learned anything interesting about the problem. And so you have to find a way to sample what we call negative edges, which are the absence of any edge between two nodes, in equal proportion with positive edges. Okay. So there's the point of this slide is to say that there's a lot of subtlety in how you would actually go about applying that simple link prediction paradigm to solve a problem in the real world, and also how you would evaluate how well it's performing. Okay, that being said, we ran some experiments. And remember, this link prediction problem isn't one of those 4 problems I outlined in the beginning. So this is kind of like a machine learning primitive. It's some simple task that we'd like to be able to solve, and then we'll use this later to solve more sophisticated problems. So you can, we compared the graph Sage neural network using just 2 layers against a 2-layer multi-layer perceptron. Excuse me. The graph Sage network achieved about 90% accuracy, whereas the regular neural network achieved about 50% accuracy, which means it essentially did no better than random. And here I'm only showing the results for the graph Sage architecture. And these numbers, I'm using twiddles because they're somewhat rough. And the idea is that, of course, these numbers will depend on your hyperparameters and how many epochs did you train for and questions like that. But typically, you'll get about 90% accuracy using the one and 50% accuracy using the other. And the top two plots are performance over the course of training, showing the loss function and also the AUC and the average precision. Then the bottom two plots are showing the AUC, which is quite good, it's 0.96. And also you might be interested in just how the probabilities are distributed. And so this is a histogram of the probabilities for the edges. Okay. So like I said, the link prediction is not one of the problems I was interested in the beginning. It was just this really common, like primitive or subroutine, if you will, that many papers have been devoted to studying. And so what I'd like to do is use this to try to solve the problem I'm actually interested in, which is network computation. And so this graph or plot shows you essentially the idea here. Step one is to generate an artificial population of people. This is to like compute the individuals that we're missing in your data set. And it'll just be individuals. You won't know how they're connected to one another. And then in the second stage, you can apply the link prediction approach I just showed you to stitch them together with themselves and with the rest of the graph. And so by combining these two steps, you can solve the network imputation problem. I'm just going to check the time. Okay. And so to solve that first part of the problem, you have to generate a bunch of artificial people or a bunch of nodes. And so this is a generative modeling task. And if you go and look in the literature, much of generative modeling is applied to the language domain or images. And probably the name that is most popular is GAN, which stands for Generative Adversarial Network. These have been used with really great success at generating artificial images of objects. I mean, the most common, I think, are people's faces. But it's true that very similar algorithms can be used to generate the data that is relevant for this problem, which is essentially a table of people, and every row in this table is going to be containing the demographic attributes we have, like their gender, their age, whether or not they're employed, and so on. So this is kind of it's not quite the same problem as a GAN is typically used to solve. And people have extended the standard GAN framework to something called conditional tabular GAN. And by the way, if you want the references, they're all at the last slide of this talk. People have extended the standard GAN to solve this type of problem. And without going into detail on how they do this, I just want to show that, a result to convince you that it's working fairly well. What I'm showing here are histograms for the marginal distributions of different node attributes. So like age, for example, gender, worker means whether or not they are employed, yes or no. And there's a whole host of these. And we have a histogram for the true data set and for the generated data set. And they're pretty close to one another. They're not perfect, which is not a surprise because you wouldn't really expect the algorithm to perfectly reproduce this, but it does a pretty good job. And I'm just looking at the marginals here. You could also look at the joint distributions, but I'm going to skip that for now. Okay, so basically by combining these two existing pieces that exist in the literature, one from generative modeling over tables and one for link prediction over these types of network data sets, you can address this network imputation problem we outlined. Okay. So at this point, I think I'm, I don't know, maybe 3/4 of the way through the talk, and I've spent all this time just talking about one problem. So to speed things up, I want to combine two of the problems and treat them at the same time. Well, actually, the reason I want to do that is because they're very closely related to one another, and it's natural to do that, but it is convenient with respect to time. So this is the problem of generating artificial graphs and taking an existing graph and like scaling it up or scaling it down, while at the same time preserving some part of the structure that you care about. And the reason why you might think that we have a shot of solving this problem without being too imaginative ourselves is that very similar algorithms exist to solve analogous problems in the computer vision domain. So I can't believe this figure is now 4 years old, but this is a figure of two artificial people spaces and this is produced using a type of GAN that researchers at NVIDIA produced. And if you think about it, an image is a type of attributed graph. The nodes are pixels, and there's going to be a bunch of attributes for each pixel representing, the intensity of red, blue, and green. And there's also a network underlying the picture. In the case of the image, it's very like a trivial network. It's like a hypercubic lattice. Whereas the problems I'm considering, it's unclear. There's not an obvious structure. It's going to be the structure that emerges when people are interacting in some city or metropolitan area. But at least, superficially, these are kind of similar data structures. And indeed, if you go in the literature, you'll find that people have adapted all the generative algorithms that are used in the vision domain to solve generative modeling problems in the graph domain. So GANs have been adapted, normalizing flows have been adapted, variational autoencoders. And there's actually been some interesting work using sequence generation algorithms, for example, recurrent neural networks, to do this task also. So in some sense, people already have algorithms to address this problem of generating artificial graphs. And, it's not fair to the people who have worked on this area for a long time to portray it as if deep learning approaches are the only approaches towards this problem. There's a long literature using other statistical models to solve this problem, and social scientists in particular use these models. Exponential random graph models are one of them. But in our research, we kind of found that all of these have this common issue of not doing a great job scaling to large N, although there are tricks you can do for any given method. So rather than trying to address that within the confines of an existing approach, we decided to try to solve this ourselves by introducing a new approach. And of course, this is a complicated generative modeling problem as you scale up the size of N. Oh, and I should have mentioned this at the beginning. The reason why these two problems are naturally connected to one another is because you can consider rescaling to be a type of graph generation where you've just changed the size of the graph. So rather than generating a graph the same size as the original, I'm going to generate an artificial graph that might be larger or smaller. Okay. So in this slide, I'm just really casually and quickly introducing our approach, which we called graph generation through iterated length prediction. And the basic idea is as follows. First step is you generate an artificial population of nodes. To do this, you can use any algorithm, but I would use the CT-GAN algorithm I just told you about. So now you have this artificial population of nodes that presumably have demographics that correspond to whatever population you're interested in. But what you don't have is how they are connected to one another. And so you can connect them as an initial step with a randomly initialized network. For example, it could be something like an Erdos-Renyi graph or a scale-free graph, whatever it is. And at that point, you're going to have a really good distribution of node data, the node attributes, but they're not going to be connected properly. So the natural solution to this is to try to iteratively rewire these connections so that the graph starts to become more similar statistically to the one you started with. And this will give you a generative model. What it really gives you is a Markov chain. And at each step in the Markov chain, you're either turning on edges or turning off edges according to the probability that your link predictor says that they should be there with. Okay. So that's a really simple generative model, and it can be used to do network rescaling just by changing the size of the population that you're putting this network on top of. And it is a very involved and subtle question on how to evaluate the quality of your generated graph. You have to figure out some way of comparing it to the existing data set that you trained on. And essentially how you answer this question is going to be it's going to be influenced by what properties of the network do you care about. Do you care about the degree distribution? Do you care about the distribution of certain node attributes? Whatever it is, you'll have to build an evaluation metric around that. One really interesting way of doing this was proposed by the Graph RNN paper, where they used this maximum mean discrepancy based on a subset of network statistics that were relevant to the application of interest. For the case of epidemiology, we've been especially focused on mixing matrices, which tell you how different subsets of your population mix with other subsets of the population. That's really important in understanding how, different subpopulations can transmit and receive the virus from others. Here I'm showing two graphs of results showing you, for example, the degree distribution of the true data in black and then generated data for different size networks in different colors. That's the top graph. And then the bottom graph is this a sort of mixing plot where the x-axis is degree and the y-axis is the average degree of the nearest neighbors. And the results, I mean, they're not great. They're not as good as I would have liked. And this is a work in progress that we're still pursuing, trying to find ways of improving this. And another issue that's not represented in these plots is that the generated graphs have far fewer triangles than the training graph. And we think we understand why this is, but it's a really tricky thing to solve it, and to solve it in a way that it doesn't break the vectorization of your algorithm. Okay, so I'm gonna move on from that and essentially step back now and try to wrap up. In the course, so this was an exploratory one-year internally funded research project, and what we did with it was looked at all the different research that people are doing within RAND, and we tried to identify 4 network problems that if we solved them or had good tools to solve them, this would be really useful across the organization and would hopefully spur an additional advances in research. With our limited time, we addressed 3 of these problems: the imputation problem, and then this combined rescaling and synthetic graph generation problem. I don't want to say we solved these problems because our generative model, although I'm happy with it, there's some problems it has that we haven't quite ironed out yet. And I want to be upfront about that. In terms of and then we have this 4th problem, which remains outstanding, and we're actually making quite a bit of progress on this, and I think we'll end up publishing this as a separate paper. This is the problem of network fusion. And just, stepping back and asking, okay, so now what? One thing I'm really interested in doing is using these methods to do the sort of simulations that I use to set up this whole line of research. So one area of research that my co-author Raf is really interested in is combining the modeling of the epidemic, where you're modeling the spread of the disease, with how people's perceptions might be affected by things like social media and their perception of the world around them. So if everyone around them is getting sick, they might be more likely to want to vaccinate themselves, as opposed to if everyone around them in their neighborhood seems to be doing really well. And this leads to a really interesting feedback between like the physics of the disease spreading and then the sort of psychological aspect or social aspect of how people perceive the threat to themselves. You can also have cases where the network is dynamic and links are only activated for short periods of time. And then another thing to do would be to combine some of the, take the best of both worlds, these traditional statistical models like ergoms, and combine them with deep learning to try to build an even better class of models. Okay, so I think that's it, and I thank you very much for your attention, and I'm happy to answer any questions.